The Advanced Heat Transfer CFD training package has 10 different CFD projects, including comprehensive training movies and files. Also, this CFD training package is prepared for advanced users of Ansys Fluent software in heat transfer area. By clicking on the subscribe button, you will be informed about the newest CFD training videos by Mr. CFD. Or if you are watching the training video, click on the Mr. CFD logo and subscribe.
In this project, we will simulate the MHD effect on fluid flow using Ansys Fluent software. By clicking on display button, a new window will appear which you can see different parts of your geometry. Also, if you click on thermal tab, you can see that the temperature thermal condition has been defined for this wall and the temperature value of 587 Kelvin is defined for this wall. If you click on UDS tab, under the user-defined scalar boundary condition, you can see that for two components of the magnetic field, we have selected the specified value. Now in the front section, you can see that we have defined two UDFs of insulating wall for these components, since, as you can remember in the previous slide, we had defined these walls to be magnetically insulated walls. And these two UDFs represent this boundary condition. After double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the compute from drop-down list and clicking on one boundary. For example, by clicking on compute from all zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. Also, in order to extract and show the path line and the streamlines of our fluid inside our computational domain, all you have to do is to right click on path line and then select new. In the appeared box, all you have to do is to select zone surface 5 under the release from surfaces, and after that click on save or display. Now in this slide you can see the path lines of our fluid inside our computational domain. You can easily see that two massive vortices have been generated inside our computational domain, which is caused by the magnetic field induced on our computational domain. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate the surface evaporation in a solar desalination system. There are several assumptions in this project and are as follows. The first, the type of our solver is set to be pressure-based. Second, the velocity formulation in this project is set to be in absolute form. And for the time, we chose the transient study since we are dealing with a time-progressing phenomenon. Also, due to the existence of buoyant forces and body forces, we have activated gravitational acceleration in y direction. In the heat mass reaction section, you will see that a changes of phases from water to vapor phase is defined, and the mechanism for this change is also defined by using a UDF, which exists in the files you will receive. Under the thermal tab, for the lateral walls, you will see that the thermal condition of convection is defined. Also, heat transfer coefficient is equal to 10, and the free stream temperature, which is the ambient temperature, is equal to 305.15 Kelvin. Also, the wall thickness for this wall is defined and is equal to 0.01 meter. Also, we have heat generation rate in this wall, which is equal to 93,500. Again, by changing the variable under the contours of section, you can see and extract different contour. Now, if you want to see different phases volume fraction for different phases available in this simulation, you have to choose the contours of phases, and in the phase section, by changing the mixture to your desired phase, you can see that phases volume fraction Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
The present problem deals with the simulation of a plate heat exchanger called Chevron. The three-dimensional geometry of the present model is designed by Design Modeler software. Since the model is related to the plate type heat exchanger, it consists of two main parts. Hot water flow zone and cold water flow zone. The boundary between these two flow paths is determined by the separator plates or chevron. The non-conformal structured mesh of the present model is carried out by Ansys meshing software, and the element number is almost equal to 640,000. Several assumptions are considered for the present simulation. The simulation is a steady state, the solver is pressure-based, and the gravity effect is ignored. As it is obvious, there are two inlets and two outlets for the CFD simulation. Two inlets for hot and cold water inlets, and two outlets for, again, hot and cold outlets. Finally, we should set the last boundary condition in this section that is related to the plate. The plate is the chevron plate. It's a stationary wall and no slip. For this case, we are going to define a plane that is Z constant and pass through the chevron heat exchanger, and it's placed on the center of the heat exchanger. So we should do the following process. Wall or chevron plate total surface heat flux could be obtained this way. Through the report section, by selecting the surface integral and identifying the area weighted average in the report type, we are able to obtain all the reports by just specifying the field variable. For example, suppose that you are going to obtain the pressure drop in the hot or cold zone. Here is the summaries of the problem definition and problem solving steps in the table as a review.
In this project, we will numerically validate the data obtained by the paper named Heat Transfer Characteristics of Aluminum Foam Heatsink with a Solid Aluminum Core. In this slide, we have extracted the figure 1 of the paper, which shows the schematic figure of an aluminum foil heatsink with a central aluminum cylinder. The airflow enters the chamber vertically and downwards from the upper section and exits horizontally from the side sections at bottom of the chamber. Inlet airflow is assumed to be developed flow, hence the height of the cylinder is assumed to be relatively high. The inlet airflow has a temperature of 300 Kelvin and has variable velocity. The purpose of this problem is to investigate the value of the Nusselt number in the porous region of the chamber in different Reynolds numbers. After clicking on the porous zone tab, we can see that the values defined for viscous resistance and inertial resistance are as you can see in this window. Under the Momentum tab, in front of Velocity Magnitude section, you can see the velocity magnitude of the fluid flow entering this boundary. You can see that the heat flux thermal condition is defined with the value of 0, which means that this wall is adiabatic. We may also change the under relaxation factors. These factors may be between 0 and 1. Based on the simulation and the project we are doing, we may change these under relaxation factors. But remember that the values set in here are the recommended values for the project, and we highly recommend you to not change these values. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the 0, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the New, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, It may be a sign that your simulation has reached convergence, but the residual must be checked as well. After double-clicking on the Residuals button, a new window will appear. In the Appear window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. Now in this contour, you can easily see the velocity distribution in our computational domain. Now in this slide, we have brought to you the formulas we had used in order to calculate the Nusselt number and Reynolds number. Now in this slide, you can see different formulation for calculating different parameters. For example, you can see that we have brought to you the total heat transfer rate as Q and formula for calculating heat transfer coefficient. Finally, after calculating all these values and parameters, you can see that in the red box shown in the lower part of the slide, we had used these parameters and then calculated the Nusselt number in this project. Finally, the summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate hyperthermia therapy of a biological tissue which is involved with a cancer tumor. The geometry of the present model is designed in Ansys Design Modeler software. The present model comprises of a cylindrical tube as the capillary, 4 spherical blood vessels attached to the capillary as tumors, and a spherical space for intra-arterial blood flow around the vein, which has a slower flow rate than flow inside the capillaries. The spherical tissues around the capillary have a different radius. The outer sphere is also considered as the space for blood flow within the tissue and around the capillary, which contains 2 input and output hemispheres. As was previously explained in the blood material, by clicking on tissue material, again a new window will appear in which you are able to change the settings for this material under the properties section. In the part big zone condition, after clicking on it, you will see that the material again is set to be blood in this zone. Also, the porous zone setting is activated. Under the porous zone tab, you will see that direction 1 and direction 2 vectors, the values for these directions are automatically set by the software, and you don't need to change or set any values. In the appeared window, you will see that the material name defined for this zone is set to be tissue. Also, you can see that a source term is activated. Under the source term tab, after double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the Compute From drop-down list and clicking on one boundary. For example, by clicking on Compute From All Zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. Now, in order to have a 3D temperature contour, just have to click on Volume Rendering button and then accept the Appear window. On the low left hand side of the software window, you will be able to change the settings for this volume rendering contour. For example, if you want to see the 3D temperature contour, you just have to change the variable to temperature. And after that, by clicking on Apply, you will be able to see the 3D temperature contour. Now, as you can see, and as was explained in the previous parts, we have defined a heat generation rate inside the cancerous cells in order to simulate the hyperthermia process. As a result of that, you can see the increased temperature of these cancer cells which is clearly shown in this contour. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate phase changing material or PCM in shell and tube wind heat exchanger. In the appeared window, you may choose between different parts of your geometry to show or not show just by clicking on them. In the solidification and melting setting, we enable the solidification and melting model. Also, in the parameters section, in front of the mushy zone parameter, we select constant and we set the value as you can see in the window. Now, the mushy zone constants measure the amplitude of the damping. The higher this value, the steeper the transition of the velocity of the material to zero as it solidifies. Very large values may cause the solution to oscillate. Now, as for the pipe wall boundaries, you will see that the wall motion and shear condition defined for this boundary is set to be stationary wall and no slip respectively. Now, in order to have a 2D contour, you just have to click on Contours button and accept the appeared window. Again, on the lower side of the window, you will see the details of Contour 1. In front of the location, you just have to select the defined plane. And in front of the variable, you just have to click on temperature. And then click on apply to see the temperature contour. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
The present problem simulates the cooling of a turbine blade. Also, all the thermal condition for all walls, all three walls, is the thermal condition equal to the convection. So for every wall, heat transfer coefficient and also a free stream temperature should be identified. The free stream temperature is equal to 1672 degree of Kelvin for the blade wall, and also all the heat transfer coefficients for all three walls is equal to 200. So we can show and display every desired contour without ignoring the geometry. This is the temperature contour in both x and y constant planes. As we can see, the maximum temperatures are near the blade and the root, and as we get close to the inner walls, the temperature decreases dramatically. The reason is that the inner wall temperature is equal to 300 degree of Kelvin. That is more than 1300 degree of Kelvin less than the root and the blade temperature. So the convection occurred, and this is the results of the temperature contour. Here is the summaries of the problem definition and problem solving steps in the table as a review.
In this project, we will numerically simulate the brake disc system conduction heat transfer. Brake is among the most widespread units with the non-stationary friction. We use braking friction system for damping the kinetic energy of the rotational or translational motion of the masses by friction forces. By braking, one can decrease the velocity of the relative sliding to zero or to the given value. In the course of operation of braking units, parameters like velocity, temperature, friction varying characteristics of material vary greatly. You can extract other 2D contours too. For example, if you want to extract the surface heat transfer coefficient of the pad, all you have to do is to select wall fluxes under the contours of section and then go over the surface heat transfer in underneath part. After that, under the surfaces section, all you have to do is to select the VAD. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, the radiation effect on a dome-shaped building is simulated using Ansys Fluent software. In the scaling part, you are able to change the mesh dimension based on your meshing software geometry you've used. For example, you've used the meter dimensions for your mesh. You can go ahead and change the scaling factors to meters, or you can change it into whatever units you want. For example, you can change it into feet, to inches, and so on. In the Appear window, under the Global Position section, you can define the longitude and latitude and time zone of your desired place. Also, you can set the mesh orientation degrees based on your preferences. You can also set the date and time of the simulation in order to make your simulation even more real. As for the final settings, you can see that the fair weather condition with sunshine factor of 1 has been selected for this project. Since you are investigating the airflow inside an enclosed area, you can see that there is no inlet or outlet in this section. For example, in this slide and next to a slide, you can see the distribution of pressure and velocity and temperature in 3D format. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
And finally, the last CFD project. Validate the article of CFD study on thermal performance of radiators in a power transformer, effect of blowing, direction, and offset of fans using Ansys Fluent software.
As for outlet boundary, you can see that the type of this boundary is defined to be pressure outlet. Just like previous steps, again by clicking on Edit, you can change the settings for this boundary. In the Appear window, in order to see different contours, you just have to select our variable first. In order to do that, under the Contours of section, we select, for example, in this case, temperature. And after that, we select our desired surfaces under the Surfaces section. After that, by clicking on Save or Display button, the software will show you the 2D contours of temperature. In this slide, you can see the temperature distribution inside our computational domain, and you can easily see how the air's temperature has increased after passing over the fins. As you can see in this slide, we have brought to you and extracted the figure 10 of the paper. Also, we have extracted and reported the value of total heat transfer in our CFD simulation. As can be seen in the graph, the experimental results obtained by the paper for the forced air convection over the fins is equal to 52.4, whereas their CFD simulation data has reported 43.58 kilowatts. And the most interesting point is that our CFD simulation is more accurate than the papers, as we have the error of 7.7%. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com.